Now let's turn everything around and explore present value. In Appendix A, there's a table of present value factors, table A2, but similar to our future value factors, they're rounded pretty liberally, so I would prefer to use formulas or use the calculator to get more accurate results for the present value. Present value is the current value of something that's going to occur in the future. So it's the current value of some future cash flows that we say have been discounted back to the present at some appropriate discount rate. Discounting is the mathematical inverse of compounding. Remember, compounding was taking your present value and multiplying by 1 plus r to the t. The present value is just the inverse of that operation. So what we've been calling the investment so far, we said we invested $1,000, it grew at some amount of interest over some number of periods. So that investment is what occurs at the present. Well, if we're given information about the future cash flows and we want to know what it's worth today, that's called the present value. So thus far, we were calculating future value by taking the present value times the future value interest factor, and that gave us that future value. The future value interest factor was 1 plus r to the tth power. Based upon this formula, we could solve for present value by simply dividing each side of the equation by that future value interest factor. So present value would be the future value divided by the future value interest factor, or simply multiplied by its inverse. So dividing by the future value interest factor is the same as multiplying by 1 over the future value interest factor. If we just rename 1 over the future value interest factor as the present value interest factor, then you'll see that that is what is represented in that table A2 in Appendix A. 1 over the future value interest factor, or the inverse of the future value interest factors, are what we call the present value interest factors. The future value interest factor was 1 plus r to the t, so the present value interest factor is 1 over that. 1 over 1 plus r to the tth power. So our present value is the future value multiplied by the present value interest factor. Let's take a $1,000 future value and discount it over 10 years' time. So if we're supposed to receive $1,000 10 years from now, what is it worth to us today? What is its present value if we discount that future value at a 5% discount rate? To get the present value, we take our future value and multiply by that present value interest factor. The present value interest factor being 1 over 1 plus r to the tth power. So r was 5%, 0.05 is a decimal, and 10 years are involved here, so our exponent is 10. So we want to get this present value interest factor so we can multiply by the $1,000 future value to get our present value. So let's calculate this present value interest factor. Let's start with the denominator. Just focus on this denominator, 1.05 to the 10th power. I want to take a base of 1.05, raise it to the 10th power. I have to use my y to the x key. So I put in 1.05, y to the x 10 equals, and that is this value here in the denominator, 1.62889. I need the inverse of that so that I will have a present value interest factor. So I can simply invert that result by pressing the 1 over x key. And that is this present value interest factor here. 1 over 1.05 to the 10th power is 0.61391. Now to illustrate that again, I clear the display. I want to take 1.05 and raise it to the 10th power. 1.05 y to the x 10 equals. I want the inverse of that, so I press 1 over x, and then I'll multiply by the $1,000 future value, and that is my present value, $613.91. So I got this factor here, 0.61391, and multiplied that by the $1,000 future value to get my present value of $613.91. Now, we'll do the same thing for our 10% result. The only thing we change is the discount rate is now 10%. So I take 1.1, raise it to the 10th power, and invert it, and then multiply by the $1,000 future value. So 1.1 y to the x 10 equals, invert it, and then multiply by the $1,000 future value, and we get the 385.54. So what's the relationship between the discount rate and the present value? How is that present value related to our discount rate when the future value is constant at $1,000 and t, the time involved, is constant at 10 years? Well, we see when we discounted at the higher 10% result, we got a lower present value. When we discounted at the lower discount rate, we got a higher present value. So certainly the discount rate and the present value are inversely related. When you discount at a higher rate, your present value will be smaller, everything else equal. I like to think about present value in terms of indifference. If you could invest money at a higher rate of interest, you could invest less today to get the same future value at some point in the future as compared to a lower interest rate. So you're indifferent between the future value and the present value as long as you can turn one into the other. The present value will always be smaller, the future value will always be higher for any positive rate of interest. But if you take the smaller present value, you can grow it into the larger future value just by putting the money on interest at whatever you used as the discount rate. Now, let's do what we did before with the future value example for this present value example. Take our $1,000 future value and discount it for 0, 1, 2, and 3 periods at 5% and verify these present value amounts. So this clears the display. Second, clear TVM, clears the third row keys. Our future value is $1,000. Now, in this case, I'm going to give up my $1,000 future value, and I'll take some smaller present value today. So let me make that negative. If I'm going to give up that future value, let me make it negative, and that will give me a positive present value. For now, the signs don't really matter. There's just some direction of cash flow. So if I put in a negative future value, my computed present value will be positive. If I did not put the minus sign on the future value, the calculator will put a minus sign on the present value. So for now, one thing's positive, the other's negative. It really doesn't make a whole lot of difference. Our answer we always want in terms of a positive number of dollars, okay? For chapter 5 and 6, certainly the present value we calculate is always a positive number. The future value we calculate is always a positive number. The plus and minus just simply mean which way the cash is flowing. So I'm going to give up my $1,000 future value to get a smaller present value today. I'm going to discount initially at 5%, 5 IY, and I'll discount initially for 0 periods. Well, we know when there's 0 periods involved, the present value and the future value are going to be the same. Again, as a double check, I can put in 0 in the payment key there, and then I'll compute my present value, and I do get the same $1,000 as my future value is. because there's no time elapsing. Now if I change the number of periods to 1 and recompute the present value, I've discounted one period at 5%, and now my present value is 952.38. And you can verify if I discount 2 periods, I'll recompute, I get the 907.03, and then 3 periods, recompute my present value, I'm at 863.84 cents. You can do the same with the 5% discount rate and verify those present value results. Now graphically, if we put the 5 and 10% results on the graph together, we'll see that when no time was involved, both the present values start there at $1,000, the same as the future value. But as we start to discount 1 or 2 or 3 periods, then the present value is becoming smaller and smaller. The 10% line is of course below the 5% line because when we discount, we're taking interest out of the investment. If I take interest out at the 10% higher rate, then the present value is lower than I would have if I discounted only at a 5% rate. So think about discounting as taking interest out of an investment. And if I take interest out at a higher rate, then the present value is going to become smaller, everything else equal. We also notice that as more time elapses, as I'm discounting for more and more periods, the present value is becoming smaller and smaller because I would be taking interest out for more periods of time. So the present value is inversely related to the discount rate, and it's also inversely related to the number of periods involved. If you discount at a higher rate, you're taking a greater percentage out. If you discount for more periods, you're taking interest out for a greater number of periods. Either way, the present value is inversely related to the discount rate and to the number of periods involved. Now think about the latter there. The present value is inversely related to the number of periods. That means if you take interest out for more periods, the present value goes down. But practically speaking, it means the longer you have to wait to receive something in the future, the less it's worth to you today. Because the longer you have to wait, the more opportunity you're missing to get your hands on the money to invest it to earn interest yourself. So the longer number of periods you have to wait for something, the less it is worth to you, everything else equal. Now, compounding within the year is perhaps the single most important concept in chapters 5 and 6. A lot of things in finance are expressed like they take place on an annual basis, but they rarely do. You might be offered a 6% mortgage on your home, but then you're told to make the payments monthly. So 6% is not really being applied to the mortgage. They'll apply 1/12 of that rate every month and charge you interest on a monthly basis. Passbook savings accounts pay interest quarterly. Stocks pay dividends quarterly, oftentimes. Bonds pay coupon payments semi-annually, most commonly. So we see that very few things in finance really happen on an annual basis, but we tend to treat them like they do when we quote interest rates because we quote the rate on an annual basis most commonly, even though things tend to not happen on an annual basis. So for example here, we're supposed to calculate the future value of $1,000 invested for 3 years at a 6% APR and then at a 7% APR. The APR, that stands for annual percentage rate, is simply the quoted rate that we're being offered. When we're told that some compounding is taking place and it's more often than annually, then we have got to reflect the, in this case, monthly compounding that takes place. So when I tell you an APR, I also need to tell you the compounding frequency. Otherwise, you really don't know the true story. So in this case, when I'm told 6% APR compounded monthly, that's not really 6%. The monthly rate would be 1/12 of that. So that's 1/2 of 1% per month. Now, we want to keep all the decimal places here, especially on that 7% result, because we'll have a bunch of decimals involved when I convert that to a monthly rate. I need to also do everything in the right number of periods. So look here, we have a 3-year investment, but it's receiving some APR that's applied on a monthly basis. So things don't happen annually, they happen monthly over a 3-year period of time. So I've got to figure out how many times I'll be paid interest over the 3 months and what rate I'll be paid each time interest is paid to me. So I'm quoted that 6% APR or annual rate, but it's going to be compounded monthly. So I've got to put that on a monthly basis by dividing it by 12. 6% divided by 12 is 1/2 of 1% per month. 6% divided by 12 is 1/2, 0.5, 1/2% per month. As a decimal, I would take 0.06 and divide by 12 and I would get 0.005. That as a percentage is 1/2 of 1% per month. Again, 6% as a decimal is 0.06. Divide it by 12 and you get 0.005 as your monthly rate. That is 1/2 of 1% per month. That rate gets applied over the 3-year time period, but interest gets paid on a monthly basis 12 times per year. So over the 3 years, there are 36 monthly periods or 36 times in which I'll be paid interest. So my future value will be calculated like this. I would take my $1,000 investment amount and multiply by 1 plus my 1/2% interest rate that is going to be paid to me at the end of the first month. This product right here will give me my future value after 1 month's time. That remains on interest because of compounding, and so that result will grow by 1/2% over the second month. So I multiply again by 1.005, and I would do that 36 times because I'll be paid my 1/2% interest every month for 36 months. So this will take place 36 times, and I'll have my future value, which would look like this. The $1,000 present value, or the $1,000 investment amount, will grow at 1/2% interest, 0.005. It will grow at 1/2% interest for 36 months. So I multiply the $1,000 times 1 plus the 0.5% interest rate applied each month, compounded 36 times over the 36 months, and I get $1196.68. On the calculator, it's fairly straightforward, but I need to get in the habit of labeling the periods here. N is the number of periods, but I need to remind myself that this is the number of months as well. Hopefully that will help me remember that I need to use the interest rate per month here, which is 0.5 or 1/2% per month. So there must be agreement between N and IY. They have to be in the same mode, if you will, the same period. In this case, a period being a month. Later in Chapter 6, we'll see that the payment has to be consistent as well. That payment has to be in the same period or the same frequency as N and IY. So for a $1,000 present value, investment amount, I'll pay that out up front, 1,000 negative PV, 36 N because I invested for 3 years, compounded monthly. I need the number of months, 36 N for the 36 months, and then 0.5 is my 1/2 of 1% interest rate per month, 0.5 IY. There's no payment involved. When I do second clear TVM, it should have set all those to 0 anyway, and then I'll compute my future value. So the calculator result, then I would do I clear my display here. Second clear TVM will clear the third row, and then I'll put in 36 N, 0.5 IY, 1,000 negative PV, 0 payment as a double check, and then compute my future value, and there is my $1196.68. The 7% APR is where I need to learn to keep my decimal points. And I also need to learn to let the calculator do more of the work. When I clear the display here, let me go ahead and second clear TVM to set everything to 0. I put in that 0 payment just as a habit to remind me it's 0 for sure. I have 36 months, 36 in. I know it's months. The calculator only knows it's 36 periods, 36 in. I write down months to remind me it's monthly. Now, I was quoted a 7% rate compounded monthly, so I need to get my monthly rate from that 7% APR, so I divide by 12. There are 12 months in a year. So I take the 7% APR and divide by 12. 7 divided by 12 gives me 0.58333 repeating percent per month. 0.583 repeating is my monthly rate in number of percent. The 7% APR divided by 12 months per year is 0.5833333% per month. Hit the IY key and it will store that in there as your monthly interest rate. 0.583 repeating percent per month. The 1,000 negative PV, like we had before, I already put in the 0 payment, so I can compute the future value and I get $12.3293. Certainly, at the 7% interest rate, I have a higher future value than I did when I was going to earn only 6%. We know future values are directly related to the interest rate. When you earn a higher rate, you'll get more money. Now, it's important to let the calculator do the work. Keep the accuracy. When you take 7 divide 12, don't round off anything. Just press IY and save all the decimal points, and you'll have a lot better accuracy that way. Now, let's look at compounding within the year for present value. In example 5.4, part B here, I have a $10,000 future value that I'm supposed to receive. My discount rate is 9%, but discounting is going to take place on a semi-annual basis. So I have to do everything on a semi-annual basis. I'm to receive the $10,000 10 years from now, but I need to be working in semi-annual periods because the discounting or compounding, whichever direction you're going, the discounting or compounding is taking place semi-annually, twice per year. So there will be 20 periods that I will be discounting my cash flows over those 10 years. 10 years, 2 semi-annual periods per year, that's 20 semi-annual periods. The discount rate I'll apply each period is my 9% discount rate cut in half. Because it's a 9% APR, it's 9% for the entire year, it's only 4.5% each semi-annual period. So I'll start by second clear TVM, and then I'll put in 20 for N and 4.5 for my discount rate IY. I make a note here that it's semi-annually, so it's 20 semi-annual periods and 4.5% per semi-annual period to make sure I've been consistent and used semi-annual for both number of periods and rate per period. There's a $10,000 future value, and I'm going to receive that in 20 semi-annual periods. So that future value gets discounted 20 times at 4.5% per period. I'll compute the present value. And again, there's no payment involved. So second clear TVM to start it out. Press the values first, then the input keys. Calculate the present value, and you should have a minus sign in front of it, because if you want to receive this $10,000 in the future, the minus sign means you would have to invest this amount at the present. So the positive future value is cash you'll receive in the future. That corresponds to having to invest or pay out 41, 46, and 43 cents today. That smaller computed present value has the minus sign, which simply means that you would pay out the 41, 46, 43 today in order to be able to receive $10,000 in the future. Now, let's learn how to solve for an interest rate. In this case, Granny gave you a savings bond that will provide $1,000 that you're to receive 20 years from now. So you'll get the $1,000 at the end of the investment. That will be a future value. She paid $214.55 for it up front. If 20 years elapse, what rate has been earned on that $214.55 to grow it into $1,000? Well, remember, we've got to tell the calculator the story, and we do that with these positive and negative or plus and minus signs, whether we receive or pay cash. She paid the $214.55, so be sure to make that negative. You'll receive $1,000. Be sure to make that positive. So to use the calculator to solve this, first do second clear TVM, and then tell the calculator the story. Up front, the present value your grandmother paid out was $214.55. The future value you'll receive is $1,000, and that's positive because it's cash you'll receive. 20 years elapse. So when we compute the interest rate, it will give us the annual interest rate that's earned on the $214.55, allowing it to grow into $1,000 over 20 years' time. The way I know this is an annual interest rate being earned is simply because I put the number of years in here as in. If I have years here for the number of periods being in years, then the computed interest rate will be the rate per year here. The calculator does not know its years involved. It simply knows 20 periods, 20 in. When I compute the IY, the calculator simply knows its percent per period. I know its percent per year because I put in the number of years. Then the computed IY will have to be percent per year. And the IY that I compute and the calculator gives me is the number 8. IY, when I computed it, is 8. I know I'm working in percent. I know it's percent per year because I put in as the number of years. There is nothing in this problem here to suggest that compounding is taking place within the year. Thus, if there is nothing said about compounding within the year, we assume it is annual. If compounding takes place more often than annually, I'd have to be told it was compounded semi-annually or monthly or daily or something like that. If there's no mention of the compounding frequency, we assume it is annual compounding. In this example, $100 grows into $300 over 5 years. And initially we'll do this for annual compounding to see what kind of rate has been earned. Remember, if the $100 is invested up front, it should be negative, and the $300 you get in the future should be positive. So second clear TVM to clear the calculator, put in the 100 negative PV, 300 positive FV, 5 years is involved. When you compute the interest rate here, it will be the rate per year because N was the number of years. In that case, the 100 grows into 300 over 5 years. It was earning 24.57% each year over the 5 years. Now, solutions to some of these can be found mathematically in the course notes, and you don't have to solve those. Sometimes they involve taking roots or using logs or something like that, just to show you the mathematics involved, and that's what the calculator has to use to solve these equations. But you can just use the calculator and not have to use logs or roots to solve these problems. Now let's look at this same problem here, and let's introduce some compounding within the year. In this case, it's periodic compounding. We're told the $100 grows into $300 over 5 years, but the compounding is taking place on a quarterly basis. In this case, I've got to do everything quarterly. Since I put in the number of periods so I could solve for the interest rate here, I'll do the same thing, but I've got to put in the number of quarters, since I'm now told that compounding takes place quarterly. So it's still 5 years' time, so I'm going to use 20 quarters because there are 4 quarters in a year. Over the 5-year period of time, there are 20 quarters involved. This is where you really want to make a note that you're working in some sort of periods other than annual, something different than a year. So for the 20 quarters involved over the 5 years period of time with quarterly compounding, 20 will be in, 20 for in the number of periods. Write down quarters though, so you remember you're working in quarters. That way when you compute your IY, you'll remember that that is the rate per quarter that you have just computed. And most likely we're going to want our answer to be in terms of the rate per year, the APR. So whatever quarterly rate I compute here, I'll need to multiply by 4 to represent it as an APR. So second clear TVM will clear your calculator. 20N minus 100 PV plus 300 FV. When you compute the IY, you'll get 5.65%. That is percent per quarter because you put in the number of quarters as the N. The computed IY will be the rate per quarter, multiply by 4 to get your APR of 22.59%. Now notice in both cases here, you're taking a $100 investment and growing it into $300. If compounding took place annually, you had to earn an annual rate of 24.57%. If compounding were to take place quarterly, the quoted APR could actually be lower, only 22.59%. The quarterly compounding did the same work, taking 100, growing it into 300 over the 5-year period of time. But the lower quoted APR, 22.59, did the same work as the 24.57% each year when compounding was annual. The quarterly compounding made up the difference and basically gave you 2 additional percentage points, right? 2 additional percentage points were earned over and above your APR here because of that quarterly compounding. So quarterly compounding gave you 2 additional percentage points compared to the annual compounding. A rule of 72 is something handy to keep in mind. If an investment's going to double, then you take 72 and divide by the number of percentage points you're earning, and it will tell you the number of years it would take to double. So if something's earning 7.2%, 72 divided by 7.2, it would take about 10 years to double. If something is earning 8%, 72 divided by 8, it would take about 9 years to double. It doubles faster than you might think because of compounding. Now in example 5.7, we're going to learn to use the calculator to find the number of periods, and it's straightforward on the financial calculator, I think. 25,000 is going to grow into 50,000. How long will that take if I'm earning a 12% annual rate? There's no mention of compounding frequency, so I assume it is annual. First, clear TVM, and then put in your 25,000 negative present value. It'll grow into a $50,000 future value, which will be positive because you'll receive the 50,000 and you have to pay out or invest the 25,000. It earns 12% per year. How many years will it take for that to happen? When I compute in, I get 6.12. Now I don't have any year attached to that. I said it was annual up top. So when I calculate this in, it's 6.12 periods. I've assumed annual compounding, so I assume that was a 12% annual rate. So it would take about a little longer than 6 years at 12% per year for 25,000 to grow into 50,000. The rule of 72 approximation can be used here because I am doubling the amount. So take the 72, divide by the 12% rate. It would take about 6 years for that doubling to take place, and the precise result was 6.12. Now, if there's compounding within the year, in this case, in part B of the example, we allow for semi-annual compounding for our 25,000 to grow into 50,000. If our 12% rate is compounded more frequently, you'll see that the amount will double even faster. Now, to reflect that semi-annual compounding, I've got to use my semi-annual interest rate. take your quoted 12% rate and cut it in half, because there are 2 semi-annual periods per year, you're going to be paid 6% after 6 months and another 6% after the next 6 months. Each year you'll be paid interest twice because the compounding is taking place semi-annually. Second, clear TVM to clear out the time value of money and put in that $25,000 negative present value and the $50,000 positive future value. 6% is your semi-annual interest rate, so 6% IY. Now, since I'm working on a semi-annual basis, I'm going to be calculating the number of semi-annual periods here. Since I put in a semi-annual interest rate, when I compute in, it will be the number of semi-annual periods. So when you compute in, you get 11.896. That is the number of semi-annual periods. It is half that many years. A semi-annual period is a half year. So 11.896 half years is half that many years, or 5.95. As you would suspect, because the compounding was taking place more frequently here on a semi-annual basis, the 25,000 doubled into 50,000 more quickly, a little less than 6 years. It took about 6.12 years when it was annual compounding. Now it's going to double in a little less than 6 years with the semi-annual compounding. So it takes less time if something is compounded semi-annually for it to double versus being compounded annually. Now let's go over the concept review for Chapter 5. At this point you might want to pause the lecture and look at the concept review questions and try to fill in the answers to them. Sometimes you'll need to set up a quantitative example to convince yourself of those relationships. And once you've done that, then restart this lecture and I will fill them in using the slides to give you the answers and what I think is correct. So see if you can complete those first before you continue the lecture past this point. Concept review for Chapter 5 consists of a lot of the time value of money relationships, and sometimes we'll need to write an example or create an example and see if the calculations confirm what we think might be the answer. So the first one says if the amount invested is doubled, then the future value will be exactly doubled. That's going to be true because of our present value future value equation that says the future value is the present value multiplied by 1 plus the rate raised to the number of periods. So if we double the amount that we invest, then we will exactly double the future value. This future value interest factor would stay exactly the same, so if we invest twice as many dollars, we'll have twice the future value. If the interest rate is doubled for a 1-period investment, then the total amount of interest earned will be exactly doubled. For a 1-period investment, that is true. Sometimes it's best to come up with an example where we just change the variable of interest, and it said specifically for a 1-period investment. So a $1,000 investment would grow to $1,050 at 5%. Doubling that interest rate, the $1,000 investment would grow to $1,100. In the first case, the interest was $50. In the second case, it was $100. The amount of interest was exactly doubled for that 1-period investment. If the interest rate is doubled for a multi-period investment, then the total amount of interest earned will be more than doubled. This is a multi-period investment, so it will be more than doubled. So let's take our same 5% and 10% example we just did, but make sure we have a multi-period example such as 2 periods, and we'll see what kind of interest we earn in that case. $1,000 earning 5% interest for 2 periods will grow into $1,102 and 50 cents. So the $102.50 is our interest. And at 10% for 2 periods, our $1,000 would grow into $1,210. So the total interest earned in that case would be 210, which is more than double the interest we earned at 5%, because with that exponent there, meaning the number of periods, when it's greater than 1, when you double this interest rate and it's raised to a power greater than 1, you will more than double the amount of interest earned. For a multi-period investment, it is more than double. For the one-period investment, the interest was exactly doubled when we doubled the interest rate. The future value is directly related to time, everything else equal. If you invest for more periods at the same rate of interest and same present value, you'll have a greater future value because you invest for more time and you earn interest for more periods. And the future value is directly related to the interest rate. As we already saw, when you increase that interest rate, you're going to increase the future value because you're going to increase the amount of interest you will earn. The present value of a lump sum, however, is inversely related to time. If you discount at a higher rate of interest, you're pulling more interest out of an investment and the present value will become smaller, everything else equal. In the lecture, we saw how a given future value, when it was discounted for more periods at a constant interest rate, that present value actually became smaller, which should make sense because the longer you have to wait to receive some amount of money, the less it's worth to you today. Or you could think about it as the longer you have to invest, the smaller amount you could take today to grow to that same future value. The present value is inversely related to the discount rate. We also saw that in the Chapter 5 lecture when we discounted the $1,000 future value at 5 and 10%. We saw that 10% line, they started out at the same $1,000, and we discounted for 1 and 2 and 3 periods at the higher 10% rate, then the present value decreased faster when we discounted at the higher 10% rate, because when you discount to calculate present values, you're pulling interest out of an investment. When you pull it out at a higher rate, the present values are going to become smaller the higher the rate that you're pulling the interest out at. The present value interest factor is inversely related to the future value interest factor. That is true. They are exactly inverses of one another. When you calculate that future value, we took our present value and multiplied by this future value interest factor, 1 plus r to the t power. When we want to take a future value and discount it, we multiply by the present value interest factor, which is 1 over the future value interest factor, or just the inverse of the future value interest factor. Now that you've completed the Chapter 5 lecture, you should complete the practice problems in the rectangular boxes found throughout the lecture. The solutions are at the end of the chapter in the course notes. You should complete the supplemental homework practice problems that are found at the end of the chapter in your course notes, and the solutions to that are found on iTunes U, where I work them using the document camera, and there's a PowerPoint file posted to Blackboard if you just want to check the answers to those supplemental homework practice problems. You should work the Connect assignment blank that is posted to Blackboard, and that is the assignment we will use to go over in class, so it provides you an opportunity to work the assignment before you actually launch Connect. You should check the syllabus for the chapters and the due date for the Connect assignment and allow yourself plenty of time to be able to complete the Connect assignment before the due date, and then come to the scheduled class session and we will go over the solutions to the Connect assignment, and you may ask any questions about that assignment if you would like. We will use that Connect assignment that we posted to Blackboard to go over during class so that everybody is looking at the same assignment, and if you print out yours or bring it on your laptop, we can look at your actual assignment during the question session if you would like. You should begin preparing for the exam early. Create your exam formula sheet as you go. Don't wait until the end. Do it as you complete each chapter. And remember that after the Connect assignments are due, We repost them for additional practice, so you may work them multiple times to help you prepare for the exams.